Hello everyone, my name is Maryam Safi and I am a student working under the supervision of Dr. Jun Chung. In this presentation, I will review my thesis project titled Design of Flight Deck Displays for General Aviation Electric Aircraft. This thesis is submitted in partial fulfillment of the Master of Applied Science program at Ryerson University's Department of Aerospace Engineering. Over the next 20 minutes, I will discuss the following topics: the thesis motivation, a summarized literature review, the study methodology, the results and their meaning, and the conclusion. Afterwards, I will discuss some future work suggestions and present the references cited in this presentation video. According to the International Civil Aviation Organization, civil aviation includes all operations except for scheduled air services and non-scheduled air transport operations for remuneration or hire. This class of aviation includes instructional flights, leisure flights, and non-commercial business flights. The design of general aviation aircraft is based off specific governmental regulations documented in various standards around the globe. In Canada, the Canadian Aviation Regulations, Chapter 523, or CAR 523 for short, are used to govern the design of these aircraft. Recently, there has been an increasing interest in converting general aviation aircraft to fully electric aircraft due to the lower emissions, operation, and maintenance cost that electric propulsion can offer. Electric aircraft gain propulsive power from electrical sources like batteries. These aircraft can be fully electric or hybrid electric, where they use a mix of electricity and fuel to power flight. At this time, very few electric aircraft are certified for operations, but a large number of concepts is under development. One of the problems in today's flight deck designs is that decisions are made for economic rather than ergonomic purposes. This creates financially apt designs that do not support the pilot when in the flight deck. The result is an increasing number of aviation accidents caused by human error. As aircraft begin to use electric propulsion, new flight deck designs need to be created to effectively communicate electric propulsion parameters. To make sure that these new aircraft are safe and effective, human factors must be applied early on in the flight deck design process. The purpose of this study is to design flight deck displays for a general aviation electric aircraft. The design will determine suitable instruments for electric power plant and implement human factors to support pilot performance. To do this research, the Alpha Electro was used as a baseline aircraft. The Alpha Electro is a two-seat, fully electric aircraft manufactured and sold by Slovenian aircraft manufacturer Pipistrel. The aircraft is certified in various regions, including Europe, Canada, and the United States of America. It is marketed for flight schools as it reduces operation costs by being fully electric. However, the aircraft can be used for recreational purposes by anyone who holds a private pilot license. Moving on to the literature review with a discussion on human cognition. In simple terms, cognition is the mental process. It includes perceiving, processing, and memorizing information. Cognition leads to the development of mental models, which are essential for human understanding and decision making. In general, cognition is a limiting factor to human performance, especially since it is related to memory and attention. With poor cognition, the risk of error increases tremendously. Human error can occur in two major forms: slips and mistakes. Slips occur when the human chooses the correct goal but unconsciously performs the wrong action. Mistakes occur when the wrong goal is identified but the intended action is carried out. A common source of errors in the flight deck is poor design of human-machine interface, or HMI. HMI design must support the cognitive limitations of humans in order to mitigate error risk. Human factors is a toolset that helps create user-centered design. Flight deck designers work to improve pilot performance, that is, ensure correct mission completion with the lowest possible rate of error. Human factors research cites many different methods of improving pilot performance. However, The most cited methods are to decrease fatigue and stress, optimize workload, and increase situational awareness. Situational awareness is the perception and understanding of elements in the environment and the projection of what could occur in the near future because of these elements. Emsley and Kaber show that situational awareness is very important for decision making. The importance of stress management in the flight deck can be best described using the Yerkes-Dodson law of human performance. As seen in the figure, human performance is highest at some intermediate value of stress, workload, or arousal. When workload is low, human performance decreases due to inattention and boredom. When workload is high, performance also decreases, this time due to feelings of stress, panic, and anxiety. Consistent periods of high workload or stress can result in fatigue, which presents a physical limitation to the human's performance capabilities. Emsley and Kaber state that automation can help improve pilot performance by increasing situational awareness and decreasing workload. Automating cognitive tasks such as memory retrieval provides help to the pilot when in high stress situations. At the same time, it allows the pilot to make decisions based on their past experiences, hence taking advantage of the creative nature of humans. Human factors specialists state that task execution should not be automated. That is, the aircraft should not inherently do things for the pilot. When task execution is automated, the pilot is forced into a monitoring role, which is a task that humans struggle to do. The pilot can then become bored and complacent, which results in low situational awareness and high chances for error to occur. Another recommended practice in the flight deck is the use of standardization for high visual clarity. Colors, symbols, and labels can be standardized to help lower the chance of confusion for pilots. In addition, keeping displays free of clutter can help pilots maintain high situational awareness. When displays are cluttered, pilot workload increases as they search for important or desired pieces of information. By keeping displays clear of clutter, pilots are able to find information quickly and easily, which corresponds to lower workload and better performance. Asmayawati and Nixon state that when designing flight deck displays, error tolerance should be accounted for. Since error-free systems are impossible to achieve, it is important that the flight deck support the pilot when an error does occur. The flight deck design done in this thesis was performed using Presage's VAPS-XT software. VAPS-XT is an industry-standard software that allows users to quickly and easily develop and prototype human-machine interfaces. The software is widely used by aircraft manufacturers and researchers as it supports touch interaction modules, various avionics standards, and much more. The design process used in this thesis is composed of 5 main steps. The first step is a literature review of existing technology and regulations. In the second step, objectives, constraints, and requirements were established as part of the design definitions. In the conceptual design stage, ideas were generated on paper, then weighed against the definitions established previously. The best fitting idea was selected and detailed out in the fourth step. At this stage, the design was created into VAPS-XT, interactions were specified, and various methods of communicating information through colors, fonts, symbols, and more was determined. Finally, the connect value method was used to test the visual effectiveness of the design during the design assessment stage. The connect value method is a mathematical calculation that gives an understanding of visual effectiveness. Basically, it allows designers to measure how well a human can understand and use information presented on a human-machine interface. The method is based on published human perception theories. The connect value K is calculated through a 2-step process. First, for each piece of information found on a display, the visual efficiency rankings are obtained from tabulated values. This gives the value RV shown in equation 1. The value Rmax is also read from these tables. Using equation 1, the visual efficiency VE is calculated for each element I as a ratio of the rankings of each element to the maximum ranking value possible. Next, each information element is assigned a weight value, W, based on how important to the overall task it is. The violations are then counted. For each design element that is inconsistent, complex in shape, or complex in color, a single count violation is added. The connect value is finally calculated using the summation shown in equation 2. To make the calculations easier, an idea box table as shown on this slide can be used to complete the connect value method. For each display screen, a single idea box table is filled out. The calculations give a connect value ranging from 0 to 1 that can be used to compare different designs or simply understand the effectiveness of a single design. Values closer to 0 indicate a more effective design. A design with connect value lower than 0.5 is seen as easier to understand and interact with. The major objectives of this study were to create a certifiable design with high visual effectiveness and user-centered automation. The corresponding requirements are to meet CAR 523 specifications, achieve a connect value lower than 0.5, and refrain from automating task execution as recommended by human factors literature. The final design of the flight deck uses 2 touch screens as seen in this slide. In normal operating conditions, the primary flight display and multifunction display appear in this fashion. The primary flight display is shown here. It includes only the flight and navigation instruments required by law on every aircraft. These are the airspeed indicator, the altimeter, the attitude indicator, the heading indicator, the vertical speed indicator, and the turn and slip coordinator. This was done to minimize clutter and distraction and improve pilot situational awareness. The display has a connect value of 0.34, which is based on the assumption that the numeric readouts in text form will be used to gather data. However, since numeric readouts are less effective at communicating quick information, pointers and scales were also added on the display in order to give pilots a better understanding of trend changes. Here is a comparison between the study-generated design shown on the left and the Garmin G1000 primary flight display on the right, which is popular in retrofitted general aviation aircraft. It is easy to see that the study design is less cluttered, especially since it eliminates the need for additional buttons and labels placed around the screen. By using a touch screen, the study design allows the pilot to directly manipulate their flight and navigation instruments, which helps match their mental model of the system to the actual system performance. The instruments are similar to existing displays to create a less steep learning curve for pilots. The motivation behind this comes from the fact that studies with older pilot populations show increased preference for older flight deck styles. In 2011, Westlin and Young reported that many older pilots experienced difficulties when adapting to the new flight deck display styles after they were trained to fly using needles and gauges. The researchers concluded that pilots prefer flight deck styles similar to those used during their training. In 2004, Fanjoy and Young had stated that training pilots with newer display styles can help them transition to larger civil flight decks more easily. This was further supported by Kolmos in 2018. Since the Alpha Electro is used as a trainer aircraft, keeping its flight deck consistent with existing flight deck displays can be beneficial to student pilots. The second screen is a multifunction display that is split into 3 sections. On the left side is the power plant indicating instrument group. It includes indicators for battery power, engine output power, engine tachometer showing rotations per minute, and temperatures of major electric components. For the Alpha Electro, there is a temperature gauge for the engine or motor, battery, and the inverter. The instruments were selected by comparing fuel-powered aircraft and electric automotive vehicles, which are the 2 most similar technologies available today. Instruments used on each type of vehicle was used to estimate necessary ones for the electric aircraft, as shown in this table. In the center of the screen is the warning display. It uses icons to communicate error warnings with the pilot. During normal conditions, icons are only shown for the major electric components, and warning icons are not visible. On the right side of the screen is the Electronic Pilot Operating Handbook, which works with the warning display to show recovery procedures when errors occur. In normal conditions, the Electronic Pilot Operating Handbook shows a main menu with topics listed in alphabetical order. The warning display icons are shown in this slide. On the left side column are the battery, engine, and inverter icons. Next to them is the fire icon, voltage icon, and temperature icon. The voltage and temperature icons can change color from amber to red to indicate warning and danger zones respectively. The icon designs borrow from existing cultural standards. For example, the battery icon is similar to the one used on smartphones and laptops. This was done to ensure that the warning display is easily understood by pilots. The warning display has a connect value of 0.07, indicating that it is very visually effective. This is because it uses color and images to indicate outlier values, which are easily perceived by the human visual senses. Here's an example of a battery fire situation. The warning display shows a fire symbol next to the battery icon, while the Pilot Operating Handbook shows the correct recovery procedure as published by the original equipment manufacturer. This automates the memory retrieval portion of the human recovery process, which is a major limitation of human cognition. The result is improved pilot performance by decreasing stress and workload. Some of the strengths of the design include the use of highly familiar and intuitive icons for the warning display. This makes the warning display easily understood by pilots. Another strength is the use of automation to support memory retrieval. By supporting cognitive limitations rather than task execution, the pilot can receive support in the flight deck while remaining in control, which increases their situational awareness and improves performance, as shown by Ensley and Cabri. Some limitations include the high reliance on visual cues. Research shows that visual cues may be missed by pilots when occurrence rate is low. This is especially true for visuals placed outside of the pilot's field of view, which may not be seen at all times. Another limitation is the use of Western cultural standards that forced a left-to-right reading convention. Although the pilot in command typically sits on the right side of the aircraft, the multifunction display was designed to read left to right as imposed by Western culture. A major limitation is the lack of pilot feedback available during the study. As a result, feedback from end users could not be collected at this time. In summary, flight deck displays were designed for a general aviation electric aircraft. The design has high potential for improving pilot performance through the user-centered automation implemented in the multifunction display. The Thesis determined indicating instruments for an electric power plant system, created a visually effective warning display, and designed an electronic pilot operating handbook to support memory-intensive tasks. The power plant indicating instruments for an electric general aviation aircraft must include, at minimum, a battery power indicator, an engine output power indicator, an engine tachometer, and a temperature gauge for each major electric component, like the battery and the engine. In the future, flight simulations with pilots will be key to evaluating the usefulness of the design. Both static and dynamic flight simulations should be performed to verify the effectiveness of the design in real-world settings. It is important to test the displays in turbulent conditions to make sure the pilot can accurately interact with the touchscreen. The design can be improved further by using auditory cues to supplement the warning display, incorporating haptics to solve touchscreen shortcomings, and using artificial intelligence to create a better warning display and electronic pilot operating handbook. Artificial intelligence modules can be used to create a self-monitoring aircraft system which can give caution messages to the pilot well ahead of time. Giving the pilot earlier warnings can help them avoid critical failures and handle errors better, as they will have more time to react to the conditions. This concludes the presentation. You can find a list of my publications that are related to this thesis on the slide. The references cited in this presentation are shown on the next two slides. Thank you for watching, and I hope you've enjoyed this video.